As neural networks scale up in complexity, standard data structures are failing to keep pace with the spatial demands of modern engines. For years, the industry standard has been the HuggingFace SafeTensors format. It does exactly what it was designed to do: store flat, linear dictionaries of matrices efficiently. But when architectures require dynamic spatial coordinates or mix different levels of numerical precision layer by layer, that flat dictionary format creates significant friction. Loom's M-POLY-VTD engine organizes neural networks as a four-dimensional grid mapped along Z, Y, X, and L axes. Every coordinate acts as an independent processing unit, allowing the engine to run 21 distinct numerical types, like 4-bit integers, 8-bit floats, and 1-bit binary simultaneously. Deploying this complex topology to devices at the edge requires a specific translation layer. We need a way to map those flat SafeTensor dictionaries directly into a rigid volumetric space. The solution is a custom binary artifact called the entity format. Without a dedicated container, the metadata and serialization overhead required to track these mixed precisions bloats the file beyond the storage and RAM limits of typical mobile hardware. A standard Hugging Face deployment usually splits a model into two pieces: a configuration JSON file to define the architecture, and separate SafeTensor files to hold the weights. The entity format merges these into a single, unified file. Opening an entity file reveals how this works. It begins by locking in an 8-byte signature, the word entity followed by 2 null bytes. Beneath that sits a JSON tree. This header defines the volumetric grid, mapping depth, rows, columns, and layer types. This section is the persistence network spec. It explicitly dictates the architecture of the neural network, documenting every parallel branch and sequential stack before a single weight is loaded. Once the structure is defined, the file transitions immediately into the raw binary payload section, which holds the numerical weights. These payloads slide perfectly into place, mapped precisely by the index paths defined in the JSON header. Because the grid uses mixed precision, every binary blob carries its own data type and scaling metadata. A 4-bit integer payload can sit directly next to a 32-bit float without any risk of misinterpretation. Housing both the architectural blueprint and the localized data types in a single file guarantees absolute state reconstruction. It ensures an edge device will never attempt to load weights into the wrong layer configuration. To use this format with existing open-source models, we use a specific ingestion process. This is handled by a function called import HF to entity. Instead of attempting to load massive models all at once, it utilizes a blockwise ingestion mechanism. Pulling in one transformer block at a time prevents massive spikes in RAM, allowing consumer hardware to compile large language models that would otherwise exceed available system memory. As each block is imported, its linear data is mapped into a 1x1x1 coordinate grid, structured into 4 specific sublayers: the prenorm, multi-head attention, postnorm, and swigglue. This mapping process elevates a standard flat Hugging Face decoder into a native citizen within the Loom framework. Once ingested as a native entity, the model is eligible for advanced operations, like spatial coordinate hopping, selective precision morphing, and topological mutation. Freeing a model from a flat layout is the mandatory first step required to execute hardware-optimized grid experiments on the edge. One might ask why a custom binary payload is necessary when Loom already supports standard JSON serialization. Storing raw weights inside JSON requires base 64 text encoding. That encoding process inherently inflates the size of every weight string by roughly 33%. To strip out that overhead, Entity bypasses base 64 entirely using encode native weights raw. It takes sub-byte types, like 1-bit binary or 4-bit integers, and packs them using bit shift operations, snapping them perfectly into a single byte without empty space. This table shows file sizes from a swigglue test suite. Across 546 runs, ENTY achieved a 28% size reduction compared to the JSON baseline. That 28% reduction comes entirely from eliminating the text encoding overhead. The numerical precision of the network remains exactly the same. This strict binary efficiency is the specific mechanism allowing heavy neural weights to run on mobile platforms like SoulGlitch without triggering system memory exhaustion. But changing a serialization format and aggressively packing sub-byte types introduces a serious engineering risk: silent numerical corruption. We must definitively prove that the data remains bit-perfect after an ENTY conversion. The answer lies in the Lucy validation suites. Specifically, Suites 7 and 8 provide exhaustive CPU-level parity testing. The methodology is straightforward. A network is built and trained, then saved in both JSON and ENTY formats. Those files are then reloaded side by side and cross-verified against each other, testing all 21 numerical types across multiple grid architectures, from single isolated cells to complex 3x3x3 structures. The logs output symbols to categorize results. A diamond indicates exact bit-perfect agreement, a green pass, or occasionally a brown circle denoting heavy drift, an expected outcome when comparing a true low-bit integer path against a float-simulated reference. In the most recent build, across 546 trained reload checks, encompassing every data type, the entity format maintained a 100% pass rate. These logs confirm that the neural state remains intact after serialization, providing the mathematical trust required for production deployments. Moving from flat tensor arrays to a verified volumetric grid is a necessary evolution for on-device deployment. The entity bridge solves the friction of flat tensor ingestion. It weaves the network's structural blueprint and physical payload together into a single cohesive file. By prioritizing native bit packing, it strips away the encoding bloat that historically kept complex machine learning architectures tethered to high-end hardware. Backed by the reload metrics in the Lucy parity suites, systems programmers have the strict data integrity guarantees they need to trust this format. This enables a direct pathway for running true multi-precision, on-device machine learning with dynamic edge topologies. The ENTY format serves as the foundational architectural container for three-dimensional multi-precision neural brains.